Welcome to the lesson on 16.2, solving exponential equations. The first thing we're going to do is we're going to solve the following exponential graph graphically, and we've done that in the past, right? We're going to use one of the equation as y1, the other equation as y2. If you look carefully, you could sort of tell that looking at this equation, this is the initial value, 275, and it's going to rise somehow. And this is 1,000, so let's say it's way above here somewhere. It's not drawn to scale, my apologies. And it's going to intersect somewhere over here. So that's going to be the y value, that's going to be the x. So you sort of get a sense of what's going on. So where would you want your y max to be? Well, if you want to see something like this, I want it to be above 1,000, say about 1,500. The minimum, I like to see the x-axis, so let's go below that, so about 200. And y max, I have no idea. So I'm just going to guess 40. And I wouldn't guess 1,000. About 40 sounds about reasonable. And I like to see the negative, so I'm going to put in -5. So I've already gone ahead and entered all the values for you already, right here. And y1 and y2. And in the windows, I already went ahead and put all the appropriate values, except I put x scale as to be 5. I don't like to see too many tick marks. For the same reason, I put a 100 over here. Hit press trace. And I could scroll left. You could see that the one in blue is y1. By pressing this, I get 1,000. You can switch back and forth. To calculate the intersection, second calc, and then press intersect, press number 5. And it's asking you first curve. Is that one of the curves? Answer is yes. Press enter. y2 is equal to 1,000. Yes. Press enter. And then it wants the intersection. I just pressed enter right away. It asks you to guess. I virtually never guess. Press enter. And most of the time it works fine. So that gives me this value right here is 21.51643. I actually like to copy all the numbers, all the values down. And it's asking for the solution. X is approximately, how about 21.52? Seems reasonable. Okay, so this is how we do it graphically. On the next page, we'll be solving this algebraically. So we learned all the rules previously, and we'll be utilizing those rules. As a reminder, the rules that we have is this. This first one, the definition-based property, this is the rule that we'll be using quite a bit. And the other one that we'll be using quite a bit is this one, power property of logarithms. One of the most wonderful properties about of the logarithm is that by having a log in the front, we are allowed to bring the exponent out to the front, like this one over here. Okay, so those two are the ones that we'll be using most. And as a reminder, I will write those rules for you. So the definition-based property is that log of base b of b to the n, it's like log base b and a b cancels, so that is n. And the other one is when you have log base b of, let's say, m to the n, it's same as having the n in the front, n times log base b of the m. So these two are the ones that we'll be using quite a bit today. Okay, let's get started. The first thing that we're going to do is actually to divide by 5 to both sides. The first is give the exact answer, right? So a, but I'm going to have a couple different approaches, so let me call it a comma I. The first thing we're going to do is divide both sides by 2. So with that yields 2 is equal to e to the 4x. So what we can do over here is to change this into convert it into the log form, right? When you do that, because it's base e, is log base e, which is ln of 2, is 4x. To solve for the x, to isolate the x, we divide both sides by 4. So x is equal to 1/4 of ln of 2. The part b says approximate it. 1 divided by 4 times ln of 2. It gives you 0.073 to the 3 decimal places. So I'm going to do exactly that, which gives me approximately 0.173. But I'm not satisfied with this. Even though it doesn't ask me to do so, you should always check to make sure that it works. Going back to this equation right here, guys, okay, I like to put my value in here. So 5 to the e, 4 times 0.173. Because x is not an exact value, this will not give me exactly 10, but should be very, very close. So 5 times e to the 4 times 0.173, I get 9.9885. But for my purposes, I'll say that's approximately equal to 9.99, which is approximately 10. Check. That's good enough for me. Now, there's a second approach that I want to share with you. A, II is exactly this right here. I like to utilize that information. Yeah? Okay. So I have 2 is equal to e to the 4x. To get rid of the base e, the base b here, I apply the log base b to that side. So what I can do is apply log base e here and log base e here as well, like this. When you do that, these two cancel. So on the right hand side you get 4x. However, what do we call log base e? That's right, it is ln of 2. Hey, we're not in the same spot. This is, no wonder this is true, because the proof of this is in fact using converting to the log form. I could do that really quickly after I finish this. So the x right here is 1/4 of ln of 2. And from here, I could see that this is true, and you do all the check work. Okay? Okay, so if you're wondering why this is the true, let's do a quick derivation on that. So log base b of b to the n is equal to n. Is this true? Okay, what we can do is express this in the exponential form. Forget this for a second. You don't see b to the n. Whatever that is if you converting to the exponential form, is b to the n is equal to whatever is in there. And that happens to be b to the n. Is this true? And answer is yes. So recognizing that, we realize that log base b of bn, b to the n, is just n. So it's canceling. Okay? All right, guys. So I think we've done enough. There are a couple more problems. So we'll do the rest in class. Have a good night.